So I will talk about innovative performance-based approach that we developed at TTI, and using the test methods that we developed, a lot of importance on pore solution chemistry. This particular approach has been implemented for Texas Department of Transportation, and I'm testing several of their SCM for the last 5 years. In the beginning of this approach, we developed a quick chemical test called a chemical screening tool, where we use two properties, two fundamental property. One is aggregate threshold alkalinity, and another one is the pore solution alkalinity of the concrete mix. And I have been talking the importance of threshold alkalinity and pore solution for several years. It's a good thing that in the morning session, people are started giving importance of the alkali threshold and pore solution alkali. That's a good thing. So it's opened a lot of collaboration, a lot of working together approach. This is a good thing. So what I do, in concrete, aggregate react with the alkaline pore solution. I try to address that particular aspect. You see over there, when the alkalinity of pore solution is high means higher than the threshold alkalinity of that particular aggregate, that reaction proceeds, it produces gel, it creates problem in a concrete. So I try to address that issue. I measure two fundamental property. One is pore solution. I will talk in my next slides that we developed a very easy way to estimate pore solution with an acceptable accuracy in a practical purpose. So we calculate pore solution called TTI Model-1. We compare with the aggregate threshold alkalinity. Now the question is how I am going to measure the aggregate threshold alkalinity. We develop a procedure which is an ASHTO standard, which did several aggregate testing, and I have a slide for that. You see the left side, option 1 is actually measured it. Option 2, if you know the aggregate reactivity in a reliable manner, use this relationship. If it is R3 aggregate, the threshold alkalinity is around 0.29. If the reactivity of the aggregate is R2, if it is on higher side, 0.38, lower side, 0.34. And then R1, very slowly reactive aggregate, it's 0.45. And almost non-reactive is over 0.52. This relationship works provided your aggregate reactivity determination is reliable. You know the false positive and negative situation. So then Excel spreadsheet use this relationship that it take the pore solution alkalinity, compare with the threshold, and try to do a lot of iteration and get a percentage of fly ash or whatever SCM you are using. It determines the percentage that you need to satisfy that criteria. Means pore solution should be slightly below the threshold alkalinity of the aggregate. This is already developed. It is an Excel tool. If you give those input, immediately it calculates how much you need. Now the question is pore solution. But before pore solution, I will talk about threshold alkalinity. This is the procedure, ASHTO procedure 364. This is an aggregate solution test. So you put in this container aggregate, loose aggregate, as received aggregate, no sample processing error, and put a solution. We prefer for reactivity prediction 0.5 normal solution. And then, this is of course, LVDT data acquisition system, a float is connected. So we measure solution volume change over time at a different level of temperature. And then we apply, of course, Arrhenius rate theory to calculate the compound activation energy, called compound activation parameter, as a measure of aggregate reactivity. The lower the CAP value, higher the reactivity of the aggregate. And you see the left side curve, the y-axis is the reactivity CAP, compound activation parameter, and x-axis is normality. We also do this test in a different level of normality. One normal, 0.5, 0.25. And you see the green line, there is a nice apparent relationship between alkali concentration in x-axis and y-axis is CAP. So we use that relationship and use that particular model to calculate the threshold alkalinity of that particular aggregate. And so this test is, of course, it is not a very simple test. It needs a very specific instruction. So we did that test and several aggregate, and you see the results here. Before coming to that, you see the results here. The left side is very highly reactive fine aggregate, and use the expansion values 1260, 1293, and our CAP best is given there. And you go to the right side, the reactivity is decreasing. The reactivity decreasing and your threshold alkalinity is increasing. So you see the left side two aggregates, the threshold alkalinity is around 0.27 to 0.3, equivalent to 2.7 to 2.9 pounds per cubic yard of alkali loading in a concrete, extremely low. Come to the middle, FA3, the value is going 0.45, 0.46. The equivalent alkali loading is 3.7. Now come to the left, very slowly reactive aggregate. You see it is around 4 pounds per cubic yard alkali loading, and the pore solution is around 0.5. So the important findings here is that current practice of fixing an alkali loading in a concrete, it's not a good idea. Alkali loading is a function of aggregate threshold alkalinity. This is a clear indication of that. Now, we develop this relationship. We calculate normality, threshold alkalinity. Using this calibration curve, we calculate the threshold concrete alkali loading. We actually made paste specimen, extract pore solution, measure the pore solution, and develop this graph. It is reasonably well for all practical purpose. So we have an idea that aggregate threshold alkalinity you can measure. And then next is pore solution. How we calculate pore solution? See, pore solution calculation NIST model is available. But the moment you add SCM, NIST model overestimate, because it assigns very high amount of soluble alkali from the fly ash and other. So it doesn't really work. For state cement mix, it really works. James thermodynamic model is super accurate, but in the real world, DOT people cannot use that. And pore solution extraction, you can do in the lab, but in the real world, nobody is going to do it. And TXDOT say that we are not going to do pore solution extraction. Give us a practical solution. So we developed this solution. This is our approach called TTI Model-1. One important thing I need to mention, that when you add fly ash in a concrete, at this time it considered inert. It doesn't contribute any soluble alkali. But in reality, that's not true. There are class C ash contributes significant of soluble alkali. There are ground glass contributes significant amount of soluble alkali. So pore solution estimation needs to consider the cement alkali and SCM alkali combined together. That's what we approach, our approach. So then, how to measure water-soluble alkali in fly ash and other SCM? ASTM, C1567, there is a little modification in NCHRP report they published, so we kind of adopt the same thing. It just measures water-soluble alkali. Means what? If there is any crystalline phase called alkali sulfate, it immediately releases into the pore solution. That's what we are picking up pretty quickly. Very easy test. So that is the quantification of water-soluble alkali from fly ash. Cement 75%, it's well accepted. Combined together, we calculate pore solution as a function of replacement of the SCM that we are using. So this is, Excel sheet is going to calculate it for you. We don't have to extract. It is all reasonable accuracy. We verified. This is the next slide. We compared. We did a lot of extraction techniques at the beginning. NIST model, James model. We did a lot of extensive work to establish our model. And you see here, NIST model is overestimating. James model and our model is very good comparison. So this really works. Then, so that means screening tool use these two parameters, pore solution and threshold alkalinity of aggregate, compare. See, the step one is our chemical screening tool. It takes only 1 to 2 days time. And I can tell you within 1 and 2 days time how much SCM you need to mitigate that particular aggregate. It's not a generalized situation. It depends on aggregate, it depends on fly ash. Now, ASTM 1567, everybody doing this test. And I want to utilize that data. You compare with the 1567. Now, chemical screening tool is a way to verify the effectiveness of 1567. We know 1567 having some limitations. I have a slide to show that. If the difference between screening tool and 1567 is less than 5%, it's okay. You don't have to do any concrete testing. If the difference is more than 5%, then you need a concrete test 1293, 2 years, and we already discussed, who is going to wait for 2 years? We develop accelerated concrete cylinder test. It takes 75 to 90 days. It's job mix. It is a job mix or standard, the same thing. You send me the concrete, I can do job mix testing. So we do that ACCT testing. What about this ACCT? This is a ASHTO standard. This is published in July 2021. We put a 3 by 6 inch cylinder inside a chamber surrounded by a soaked solution. The chemistry is equal to the poured solution chemistry of that concrete. It's a matching. So it's a pretty good equilibrium. 60 degrees Celsius temperature. Length change is measured using an LBDT data acquisition system at 60 degrees inside an oven. It's pretty accurate. No human error of data. Of course, somebody has to pay a computer cost, data acquisition cost, a little bit knowledge on how to operate. That's it. But it's super accurate test. Now, why I do ACCT testing? You have this 1567, 1293. The only problem with these two tests, we add bunch of alkali to elevate the alkali level in a concrete, in a mortar specimen. When you elevate the alkali level, it is a common sense that you are using an SCM which contributes soluble alkali a little bit. How you are going to pick up that information when is already added bunch of alkali in a mix? That's why ACCT is taking care of that. ACCT is matching. So it's going to detect the soluble alkali contribution from SCM, not only cement, but SCM, and also job mix. You send me a job mix, a cylinder 3 by 6, I can test it. We did conventional ash. You see the results, category 1. Chemical screening tool, 1 to 2 days. 1567, 14 days. And ACCT, 75 to 90 days. 64% a good match, right? 64%, there is no worry, all are giving the same results. What about the 36%? 1567 underestimate. And why? Because alkali boosting situation, it cannot pick up the soluble alkali contribution from SCM. That's why it's giving a flat 20, 25. But sometimes the difference is more, almost 10 to 12%. So that means we have a mechanism. You give me 1567 results, I will apply my chemical screening tool and tell you right away, is it the results are acceptable, is it accurate? Quickly check it. If it is not, then you need a concrete test. Now somebody can, ACCT is a costly test. I'm not recommending ACCT for all. I have a screening. I screen it. You send 20, maybe ACCT 5 I will do, maybe 4. Remaining 15, I will take a decision within 14 days. Now, this is an important slide. Blended ash. It's an alternative, right? Blended ash. The first one is 50-50 blend class C and pumice. It qualifies as a class F based on 618. We did the test. Screening tool, ACCT. It needs around 40%, 40 to 45%. You don't need 40% class F ash. Why 40%? Because original component is class C ash, it's contributing soluble alkali. Pore solution is going up. You still need 40 to 45, like a typical class C. So as far as the ASR is concerned, it behaves as a class C, but it qualifies as a class F based on 618. This point needs to be noted. Now, second blend is PRB 80% and lignite 20% blend. You see, this is qualified. This is based on CAO 18.3. It's a class C, almost class C ash. But because it doesn't contribute any water-soluble alkali, a 30% is good enough. So although it is sounds like a class C, but it is behaving as a class F. So class C, class F terminology really has no relevance. The relevance is it how much is modifying the pore solution alkalinity of concrete. Fundamental. You don't have to go class C or class F or anything. Any alternative material can be tested with this approach. Now, this is all natural pozzolan. You see the all bunch of natural pozzolan. The only thing I need to highlight here, you see the bulk alkali content extremely high. Now the common question is, oh, bulk alkali concentration is very high, so I'm nervous. We have a good information based on fundamental approach. These all natural pozzolan content feldspar, mica, a crystalline phase, bunch of alkali bounded in those crystalline, those are almost insoluble in a short term. Alkali sulfate, which contributes soluble alkali, are extremely low. Now, you see comparative assessment. Natural pozzolan, class C, class F. Natural pozzolan, those crystalline phase doesn't contribute any alkali. So soluble alkali is very low. Now, alkali binding, that is a very important parameter that we are not. Alkali binding, natural pozzolan produce pozzolanic product which consumes alkali from the pore solution. So that reduction. So net effect, natural pozzolan, it doesn't modify the pore solution, it doesn't elevate. That's a good thing. Class F, intermediate. Class C, you see class C, there are soluble crystalline alkali sulfate phase. This contributes soluble alkali 14 to 17%. Alkali binding effect class C is low than the class F. So ultimate enhancement of the concrete pore solution by class C is high. Because this is high, you need higher percentage of replacement. Because it is intermediate, you need intermediate level of replacement. Because natural pozzolan doesn't modify pore solution. Although bulk alkali content is extremely high, you still need a lower percentage to mitigate a highly reactive fine aggregate. I have a slide for that. You see here, left side is water-soluble alkali. Natural pozzolan very low. Class C, F, intermediate. Class C, high sometimes. Variability, of course, very high variability. Now, this is available alkali based on ASTM C1567. Similar relationship. So the good thing here, natural pozzolan doesn't contribute soluble alkali or very negligible amount. Now, you see this is the screening tool. See, the y-axis is the pore solution chemistry. X-axis is the different, and then the PSA, if you don't add any SCM, the pore solution of the concrete is around 0.5. Now, the moment you add different SCM, pore solution is going to go down, go down, go down. And compare with the green line, the aggregate that I use, which is highly reactive fine aggregate, the threshold is 0.335 normal. So to achieve 0.335 normal, you need around 25% natural pozzolan. To achieve the same threshold, pore solution alkalinity, you need around 35% class F ash. But for class C, you need 45 to 50%. The answer is pore solution modification. Aggregate is fixed here. You are changing different SCM, how it's modifying pore solution, and compare with the threshold, that determines how much percentage you need. This needs 1 to 2 days time. Now, the horizontal line is different reactivity. R0 is a non-reactive, R1 is a slowly reactive, R2 is a highly reactive, R3 is a very highly reactive. R2 we tested. R3, if the reactivity goes up, your percentage requirement is going to go up because of the pore solution and threshold relationship. This is very clear. So that means what? A percentage requirement for an SCM depend on the SCM characteristics, and aggregate reactivity means aggregate threshold alkali, these two parameters. Now you see here the results. We predicted based on chemical screening tool all those natural pozzolan, these are the values, compared with 1567, compared with our ACCT test. All are good match, even though natural pozzolan bulk alkali content is high. That's a very important thing. Now, this is an important slide, ground glass. See the ground glass, 30% ground glass failed by 1567 ACCT. 45% ground glass ACCT failed, but 1567, 14 days say pass, but 28 days, no. So ground glass alone is not sufficient to mitigate a highly reactive fine aggregate. Why? Because ground glass contributes soluble alkali in the pore solution. But see the ternary blend? So if you want to use ground glass, the best way to use is ternary blend. You see the 22% ground glass and silica fume, ground glass colloidal silica, ground glass metakaolin, 25% ground glass and 15% metakaolin is fully mitigated by our ACCT, which is also supported by 1567. But if you don't do ACCT, only 1567, 14 days, you are going to end up creating a problematic mix. So this is the limitations of 1567. If the SCM that you are going to use, it contributes soluble alkali in pore solution. So this is the conclusions. The applications of chemical screening tool, the pore solution supposed to be slightly lower the threshold alkalinity criteria was validated to determine the dosage of natural, this is for natural pozzolan and conventional ash and unlimited alternative SCM, including ground glass, for a highly reactive fine aggregate. Although the bulk alkali contents of the studied natural pozzolan is high, their soluble alkali contribution to the pore solution was found to be low. The water-soluble alkali trend and the percentage requirement is good match. That means answer is some SCM contribute soluble alkali in pore. That is the key to understand. That is the fundamental science to determine the percentage. And that takes only 1 to 2 days time. Then we validated based on 1567 14 days test, ACCT 75 to 90 days. It's a pretty good match, this approach. Now the important thing is 1567 is recommended that sodium, if any SCM, sodium equivalent is more than 4.5, you should not do 1567. That's the current recommendation in ASTM. The reason, we now know the reason. If it contributes more soluble alkali, don't do 1567 because it may confuse you for sure. And so, a combined approach of CST and ACCT with judicious use of AMBT can reliably determine the optimum NP dosage and all conventional, all other, any kind of alternative SCM, because I am not restricted by anything. You send any unknown material, I'm going to, because I just calculate pore solution and save time, money, and increase the reliability. I can tell you that whatever I'm telling you, it takes only sometimes 14 days, maybe a month, sometimes 75 to 90 days. And I'm telling you something with a good confidence. This approach I implemented for TxDOT 5 years back. They are very happy with it, and I have been testing several of their SCM for the last 5 years. So my focus is using this approach to do SCM optimization, any kind of SCM, any ternary blend, binary blend, whatever you want, we can do it within 90 days max. These are my sponsors. Texas Department of Transportation is a great support for me. I'm working with them since 2010. I'm still working for them. There are some money came from different other sources. And thank you.